Hi, my name is Ron Lynch. I do web handling training and consulting. Developing a new web path can be an overwhelming experience. There are many questions that need to be answered and boxes to check before the first check is written. This presentation is an outline on how to get started. There are several things you must do when developing a new web path long before the first roller is purchased. I had a sign above my desk that said, "The web is not your friend. It does not care about your schedule, your budget, or your career. It is selfish. It will do what you want only after you give it everything that it wants first." To begin with, you'll need to be web centric and not think about machine design or anything else yet. You have to start with identifying the needs of the web and process. My checklist for getting started begins with understanding the tensioning and transformation requirements of the web, anticipating wrinkle and tracking needs, planning how to meet the phase and registration requirements for your product, addressing dynamic issues, and these are things that are affected by speed or acceleration like air entrainment, idler drag, inertia, and drive control. And finally, you can do everything else. I'll cover each of these items in turn. The two best tests to determine what the web needs are tensile test and camber test. The objective of these two tests is to define the design range and failure limits for tension and strain of the web. The first thing you will want to do are tensile tests to produce stress strain plots. Not one, not two, but many, many plots. The first test is to pull the web until it breaks. From this you can see where the web is linear and where it breaks. But you can't stop there. You'll need to do several different types of tests to fully explore the web's properties. From the first plot, we can estimate that our design range will be somewhere in the linear or nearly linear portion of the plot. The upper end of the design range will probably be 10% to 25% of the breaking strain, but we'll need to test more to make sure. We'll do a second test with a new sample pulling first to some fraction of the expected design range, maybe 1/5 of the way, and then quickly relax the sample back to zero strain. Then we'll do a second pull using the same sample, never unclamped, to a higher strain, maybe 2/5 of the way through the expected design range, and again quickly relax it to zero strain. What we are looking for is how fast the web recovers from strain, that is, its viscoelastic behavior. We'll look at the ratio of the peak strain we pulled to the strain where the tension returned to zero during relaxation. The ratio of these two strains is important. There is no official name. I call it the instantaneous strain recovery ratio, the ISRR. When your web goes from high strain to low strain over a driven roller, it needs to recover very quickly. This test gives you an idea of the web's ability to do that. We can keep going with a third pull. Again, watch the strain recovery ratio. And a fourth pull. And a fifth pull. A third test on a new sample is to allow the web to fully relax between each cycle to see if there is permanent deformation and at what peak strain it starts, and the ratio of the permanent deformation to each peak strain. If the web recovers to its original length, all of the strain was viscoelastic and there is no permanent deformation. If it does not recover to its original length, there is some permanent deformation. So what did you learn from this? You learned about the breaking strain and the web's tension behavior. You learned if the web is linear elastic or nonlinear, non-elastic, and if you can use simple linear elastic math. You learned about its viscoelastic behavior and how fast the web recovers from strain. You learned about permanent deformation as a function of strain. You still need to define what is significant permanent deformation and where to stop, but that is a product design question. You can do variations of this kind of testing to answer all of your web behavior questions. You're learning what your web wants and what it can do. If we take all that we have learned so far and put it together, we can pick the upper failure limit. I usually pick something based on significant permanent deformation. You have to decide what is right for your situation. We know there is a lower strain failure limit, but we need to do another test to identify that. And between the upper and lower failure limits, there's a design range, and we still must specify that. The next thing we're going to do is a camber test to measure the radius of curvature of the web. A cambered web runs with a loose edge, and you'll need to apply enough tension to pull out the looseness. If you know the radius of curvature, you can calculate the required strain and tension. To do a camber test, roll out a length of web, usually on the floor. How much depends on the web and the amount of camber. I've seen as little as 10 feet and as much as 70 feet used. Flatten the web on the floor without stretching it or influencing its natural shape. Then use a string as a straight edge and measure the bow height in the center of the length. From this, you can calculate a radius of curvature, and then you can calculate a minimum strain and tension to avoid loose edges. We can use this as our lower failure limit. Camber is a specific type of dimensional imperfection. What you are after is how much strain does it take to make the web flat and straight. If you have other dimensional imperfections, pull the web until it is straight and flat and use these values as the lower failure limit. There may be other things like sag and long spans and traction with idlers that can also define the lower failure criteria. Transformations may have some specific requirements for tension and strain. In printing, for example, the length of the plates is based on an expected amount of strain in the web. A slot coder is tension sensitive. Another thing about transformations is that they change the web. You will need to know how much they change the web's properties. You may need to do a whole nother set of stress strain tests and camber tests to understand the new web's properties. Now you can put together a first draft of a web path to think about the order of events and other needs. It's time to think about what tension you need for your unwind and splice system, about wrinkle and tracking needs at transformations, and about the placement of wrinkle remover rollers and tracking guides. You will also need to consider physical space requirements like transporting a web through a long drying tunnel or needing a multi-dimensional path to minimize the footprint of the line. Now you can start to think about control schemes for tension control and phase and registration systems. You need to work out the locations of sensors and control rollers. Now that you have an idea of your maximum tension, you can start to think about idlers. Get estimates for drag and mass either from vendors or past experience. A tension plot plots tension or strain for each span in the path. Strain or tension is plotted on the y-axis and span number is plotted on the x-axis. You can plot either strain or tension, that's your choice. We have already found our failure limits. Now we need to think about the design range. Several factors go into the spread and positioning of the design range. The one we talked about so far is the instantaneous strain recovery ratio. Since the recovery ratio is the ratio of the peak tension to zero tension, we can't design to the full ratio but must apply a safety factor. For this presentation, we'll simply use 2. So if the ISRR was 6, we'll set the design range to be a 3-to-1 ratio between high tension and low tension. Another thing to consider is the tension ratio that can be supported by friction if you use friction drive rollers. You can design friction drive rollers to have a TH over TL equals e to the mu theta ratio that is wide enough to span the design range times a generous safety factor. Lastly, large tension drops over driven rollers can cause wrinkles, especially in wide, thin, flexible webs that neck down. This can also limit the design range spread. For now, we'll center the design range between the failure limits and adjust it later if needed. To use the tension plot, target the first span's tension near the low end of the design range, allowing extra tension if needed to overcome blocking and to avoid slack web during splices. The second span is higher than the first due to the drag of the idler between. The third span is again higher than the second due to the idler's drag between them. If a third idler is added, the fourth span's tension would need to be higher than the upper design limit, so instead of a third idler, a driven roll is needed. The fourth span downstream of the driven roller starts low, and the web again starts the climb towards the upper limit and the next driven roller. Plotting tension roll by roll continues to the end of the path. You can make adjustments and place driven rollers for special process needs and transformations along the way. But wait, there's more! I always recommend a model. A simple Excel model can be used to do sensitivity studies and what-if analysis. It can check how sensitive the path is to normal variation of modulus, coefficient of friction, velocity, and to changes to tension and roller speed set points. It can be used for cost versus flexibility versus risk studies by looking at raw materials and other changes that might be made over the life of the machine. Now you can add normal variation to the plot. If needed, you can adjust the design range up or down and add or remove rollers. Make paper changes now to avoid making equipment changes later. Making it work here doesn't guarantee success, but it does improve your odds. This is also a good way to visualize and illustrate the choices you make. Now you are ready for the final layout. Now that you know what tension is applied to all the rollers, you can modify the original roller designs if necessary. Also, knowing the tension on all the rollers, you can check for air entrainment issues. You can ensure that you have adequate traction on all the rollers, and you know that you are able to run the range of modulus expected under normal variation. Lastly, you are future-proofed or have a plan to adapt. Finally, by the nth draft, you are satisfied that all your web's needs will be met and you have a web path that you can run with. Now you're ready for design. Now, I'm not a machine designer, so this is as far as I go. Are there any questions? Hopefully, I'm online to answer questions. If not, an email is fine with me. Thank you for listening, and I hope you find this helpful.